All right, welcome to the deep dive. Today we're gonna get into some real nitty-gritty stuff. We're talking about
Mm.
mechanical engineering, but like really taking a deep dive into what things are made of and
Yeah.
how we can move them around with the power of fluids,
Mm.
like hydraulics and all that.
Yeah. And the material you guys sent in is really all over the place. You've got like the basic science of materials, like what they're made of at the tiniest level. And then you've got these giant systems using fluids to move mountains, basically.
Exactly. So it's a huge range
Yeah.
from the microscopic to the macroscopic. And our mission, I guess you could say, is to really pull out the most important stuff from all this. What's going to be most interesting and helpful for everyone listening. But we don't want to just lecture you. We want to have a real conversation about it.
Yeah, for sure. So why don't we jump right in? First up is engineering materials, the stuff that everything's made of. Your sources break it down into like five main groups: metals, polymers, which are basically plastics, ceramics, composites, and semiconductors.
I think a good place to start is metals. Everyone's familiar with those.
For sure, metals are everywhere. So what makes a metal a metal?
Well, think about it like this. You see a shiny wrench, right, or a copper wire that bends. That shine, the fact that it conducts electricity so well, that's all because of how the atoms are bonded together. It's called metallic bonding. And usually metals are strong, but you can still shape them, bend them, stretch them. That's what we call ductile and malleable. And then they melt at super high temperatures and they're heavy.
Yeah, okay, that makes sense. And there are pure metals, and then there are alloys, right?
Exactly.
And your sources mentioned some good examples, like aluminum. It's everywhere: cans, window frames, even airplane parts. And it's so popular because it's strong for how light it is, and it doesn't rust easily. Corrosion resistance, that's the key. And that's also why they use tin to coat things. It's like a little shield against rust.
Makes sense. And speaking of high temperatures, what about tungsten?
Ah, the old school light bulb filament. Tungsten can take the heat, and it won't corrode either. It's perfect for that job.
Right, right. Okay, so we've talked about pure metals, but what about alloys? Like, why even bother mixing metals together?
Well, it's all about getting the best of both worlds. Like sometimes you want a metal that's even stronger than a pure metal, or maybe harder, or more resistant to certain things.
I see. It's like combining superpowers, kind of.
Exactly.
So give me some examples. I know steel's an alloy, right?
Yeah, steel's a classic one. Then you've got stainless steel, which is even more resistant to corrosion, and high-speed steel, which they use for tools that get really hot, like drill bits. Oh, and brass.
Oh, yeah, brass. So many instruments are made of brass.
Oh.
Okay, and your sources mention a couple others like duralumin.
Yeah, duralumin is a mix of aluminum, copper, magnesium, and manganese. It's super strong, but still light, which is why they use it in aircraft and some vehicles. And then there's bell metal, a type of bronze made with copper and tin. It's used for casting because it's strong, tough, and can be machined easily. Plus, it rings beautifully.
I can almost hear it. Okay, that's metals. What about polymers? I know they're basically plastics, but what makes them different?
Well, polymers are made up of these long chains of carbon molecules. It's a totally different structure than metals. And one big difference is that they're really good insulators. They don't conduct electricity or heat well. Like the handle on a frying pan, it's plastic, so you don't burn yourself.
Yeah, good point.
Uh,
There are
s-
different kinds of polymers, right?
Yep. Your sources talk about three main types: thermoplastics, thermosetting plastics, and elastomers.
Okay, break those down for me.
Sure. Thermoplastics, these are the ones that can be melted and remolded over and over again. Think of like PVC pipes or soda bottles. They're often recyclable, which is good.
Yeah, gotta love recycling. Okay, what about thermosetting plastics?
Well, unlike thermoplastics, these guys, once you heat them and they set, they're done. They won't melt again. They're harder and stronger than thermoplastics, like Bakelite, which they used to use for a lot of things: phone cases, appliance parts, stuff like that.
Interesting. And last but not least, elastomers.
These are the stretchy ones. Think rubber bands or tires. They can deform a lot and then bounce right back. Great for absorbing shocks and vibrations.
Okay, makes sense. So we've got metals, polymers. What's next? Ceramics.
You got it. Ceramics are a whole different animal. They're compounds made from metals and nonmetals, usually oxides, carbides, or nitrides. Like that super hard tip on a drill bit, that's probably tungsten carbide.
Ah, okay. So they're known for being hard. What else?
Well, they're great insulators too, both for heat and electricity. And they can handle really high temperatures, and they don't corrode easily. The downside is that they're brittle. You drop a ceramic plate, it shatters.
So strong but fragile.
Yeah.
And what were those other examples?
Oh, right. Well, besides tungsten carbide, there's aluminum oxide and silicon nitride. And then, everyday stuff like glass, cement, and sand.
Okay, so ceramics are all around us too. Now, what about those semiconductors? They sound kind of mysterious.
They are kind of cool. So basically, they're materials that conduct electricity, but not as well as metals. They're somewhere in between a conductor and an insulator, hence semiconductor.
Okay, that makes sense. Where do we see semiconductors?
Well, pretty much all electronics use semiconductors.
Yeah.
Phones, computers, TVs, you name it. Silicon and germanium are the most common ones.
It's amazing how these tiny things power so much of our lives.
But they do have some of the same drawbacks as ceramics, right?
Yeah, unfortunately, they're not great at conducting heat, and they're brittle too. Not very strong either. It's kind of a trade-off.
Yeah, I guess every material has its pros and cons. So speaking of which, let's talk about material properties in general. Like, what are the different ways we can describe how a material behaves? Well, your sources group them into 5 categories: mechanical, electrical, chemical, thermal, and physical. Basically, how it reacts to different forces and environments.
Okay, let's start with mechanical. I mean, those seem pretty important for engineers, right?
Absolutely. Mechanical properties are all about how a material responds to forces, pushing, pulling, twisting. We're talking about things like strength, which is how much force it can take before it breaks. Then there's the elastic limit, which is how much you can bend it or stretch it, and it'll still spring back to its original shape.
Yeah, like a spring. And what about stiffness? How do we measure that?
That's the modulus of elasticity. The higher the modulus, the stiffer the material. Like steel has a much higher modulus than rubber.
Right. And then there's ductility versus brittleness, right?
Exactly. Ductility is how much a material can deform without breaking. Like you can draw a wire out of copper because it's so ductile. Brittleness is the opposite. It breaks before it bends. Think of a glass rod snapping.
Okay, I'm getting a good visual there. And what about toughness? I feel like I hear that word thrown around a lot.
Toughness is all about how much energy a material can absorb before it fractures. It's measured in joules. Ductile materials tend to be tougher because they can deform more before they break, absorbing more energy in the process.
Interesting. So a tough material can take a punch, so to speak. And what was that last one? Hardness.
Yep. Hardness is how resistant a material is to scratching or denting. The harder the material, the more difficult it is to scratch. Like diamonds, they're the hardest natural material.
Right, I've heard that diamonds can only be scratched by other diamonds.
Exactly. And that hardness comes from the very strong bonds between the carbon atoms.
Yeah. Okay, moving on to electrical properties.
Sounds good. What do we talk about there?
Well, mainly conductivity and resistivity. Basically, how easily electricity flows through a material. Metals are excellent conductors, which means they have low resistivity. Polymers and ceramics, on the other hand, are typically good insulators, meaning they have high resistivity. Okay, so it's like the opposite of conductivity. And what about dielectric strength?
Ah, that's a good one. Dielectric strength is how much voltage a material can withstand before it breaks down and starts conducting electricity. Think of the insulation on electrical wires. You want it to have a high dielectric strength so you don't get shocked.
That makes sense. And how do polymers and ceramics stack up in terms of dielectric strength?
They generally do very well, better than metals at least.
Okay, so they're good insulators in multiple ways. Now, what about chemical properties?
Well, when we talk about chemical properties, we're mainly concerned with how a material interacts with its environment. And the big one here is corrosion.
Corrosion. Yeah, that's like rust, right?
Exactly. It's basically the gradual degradation of a material due to chemical reactions, often involving oxygen. It can be a big problem for metals, but luckily there are ways to prevent it or at least slow it down.
Like painting.
Yep. Painting's a good one. And there's also galvanizing, which is coating the metal with a layer of zinc, and things like cathodic protection, which involves using sacrificial anodes to attract the corrosion.
Interesting. And how do polymers and ceramics fare when it comes to corrosion?
Oh, they generally do much better than metals. They're naturally more resistant to those chemical reactions.
That's good to know. All right, so we've got mechanical, electrical, chemical. What about thermal properties?
Thermal properties deal with how a material responds to heat. So one important one is the coefficient of linear expansion, which tells you how much a material will expand or contract when the temperature changes.
So like railroad tracks expanding the heat.
Exactly. And different materials expand at different rates. Polymers tend to expand the most, followed by metals and then ceramics.
Interesting. And what about specific heat?
Specific heat is the amount of heat energy needed to raise the temperature of a certain amount of a material by a certain amount. So a material with the high specific heat can absorb a lot of heat without its temperature changing much.
So, like, water has a high specific heat, right? That's why it takes so long to boil.
Exactly. And polymers and ceramics generally have higher specific heats than metals.
Good to know. Okay, we've covered a lot of ground. What's left? Physical properties.
Yep. Physical properties are the more, I guess you could say, basic ones, like density. That's just how much mass is packed into a given volume. So lead has a much higher density than, say, wood.
Right. And what about specific strength?
Specific strength is the strength of a material relative to its density. It's a useful measure for comparing materials when weight is a concern. Like in aerospace, you want materials that are strong but also lightweight.
Makes sense.
Yeah.
All right, we've talked about all these different properties, but what really determines how a material behaves?
Well, at the most fundamental level, it's all about the structure of the material, how the atoms are arranged.
So it's like the architecture of the material.
Yeah, exactly. And there are two main types of structure, crystalline and amorphous. In crystalline materials, the atoms are arranged in a very ordered, repeating pattern. Think of like a honeycomb.
I see. And what kinds of materials have a crystalline structure?
Most metals, alloys, some ceramics, and semiconductors.
Okay. And what about amorphous materials?
Amorphous materials have a more random, disordered structure. Like glass is a good example of an amorphous material. And many polymers are also amorphous or partially crystalline, meaning they have both ordered and disordered regions.
Okay, so the arrangement of atoms really dictates how a material will behave. Fascinating.
It really is. Okay, so that was a whirlwind tour of materials, ready to dive into the world of fluids.
Let's do it. It's kind of a different world, but still totally essential to mechanical engineering, right?
Absolutely. Fluid power is everywhere. From the hydraulic systems that move heavy equipment to the pneumatic systems that power tools and robots, it's all about harnessing the power of fluids to do work.
Okay, so first things first, what exactly is fluid mechanics?
Fluid mechanics is the study of how fluids, liquids, and gases behave, both when they're at rest and when they're in motion. It's a fascinating field that combines physics, math, and engineering principles to understand and predict the behavior of these, well, fluid substances.
And there's a big difference between liquids and gases, right?
Absolutely. Liquids are generally considered incompressible, meaning they don't change volume much when you apply pressure. Gases, on the other hand, are compressible. Think of squeezing a balloon. You can compress the air inside.
Makes sense. And what are some of the key properties of fluids?
Well, there's density, which is just the mass per unit volume. How much matter is packed into a certain space. Water has a density of about 1,000 kilograms per cubic meter. Air is way less dense at about 1.23 kilograms per cubic meter. And mercury is super dense at 13,500 kilograms per cubic meter.
Okay, so mercury is like really heavy.
Yeah, it's like liquid metal. We also have specific weight, which is just the weight per unit volume, and specific gravity, which is the ratio of a fluid's density to the density of water.
Okay, and then there's viscosity, like how thick or runny a fluid is.
Exactly. Viscosity is the fluid's resistance to flow. High viscosity means it flows slowly, like honey. Low viscosity means it flows quickly, like water. It's all about the internal friction within the fluid.
I see. And there's even a law for that, right? Newton's law of viscosity?
Yep. It basically describes how the viscosity of some fluids changes with temperature and pressure. And based on this, we can categorize fluids as either Newtonian or non-Newtonian. Newtonian fluids, like water and air, have a constant viscosity no matter how fast they're flowing.
And what about non-Newtonian fluids? Those sound kind of weird.
They are. Non-Newtonian fluids don't follow the rules. Their viscosity can change depending on the force applied to them. Like oobleck, that cornstarch and water mixture, it acts like a solid when you punch it, but then flows like a liquid when you let go.
That's so cool. Okay, so we've talked about viscosity. What about pressure? Like, what is pressure in a fluid?
Pressure is the force per unit area that a fluid exerts on its surroundings. It's measured in pascals, or sometimes bars. And one of the most important concepts here is Pascal's law.
Okay, tell me about Pascal's law.
It basically says that if you apply pressure to a confined fluid, that pressure is transmitted equally in all directions. So like if you squeeze a tube of toothpaste, the pressure you apply at one end is felt throughout the entire tube.
Ah, okay. And what about absolute pressure versus gauge pressure?
Well, absolute pressure is the total pressure, including atmospheric pressure. Gauge pressure is the pressure relative to atmospheric pressure. So, like when you check your tire pressure, you're measuring gauge pressure.
I get it. And speaking of measuring pressure, your sources mentioned something called manometers.
Yeah, manometers are simple devices used to measure pressure differences. They basically work by balancing columns of fluid. There are different types, like U-tube manometers, single-column manometers, and incline manometers. They all work on the same principle, but they're just designed a little differently depending on the application.
Got it. So we've talked about fluids at rest. What about fluids in motion?
Ah, that's where things get really interesting. When a fluid is flowing, we can have different types of flow. There's laminar flow, which is smooth and orderly. The fluid particles move in parallel layers, kind of like cars on a highway.
I can picture that. And then there's turbulent flow, right?
You got it. Turbulent flow is chaotic. The fluid particles are swirling around in all different directions. It's like rush hour traffic, with cars weaving in and out and changing lanes.
That's a good analogy.
Mhm.
And what determines whether a flow is laminar or turbulent?
Well, several factors, like the fluid's viscosity, the speed of the flow, and the geometry of the channel it's flowing through. But there's this handy dimensionless number called the Reynolds number that helps us predict whether a flow will be laminar or turbulent.
Okay, so the Reynolds number is like a predictor of chaos.
You could say that. A low Reynolds number means the flow is smooth and well-behaved, like honey flowing out of a jar. A high Reynolds number means it's going to be turbulent, like the rapids in a river.
Cool. So how do engineers actually analyze fluid flow?
Well, they use a bunch of different concepts and equations. Like we talk about uniform flow versus non-uniform flow. Uniform flow means the velocity of the fluid is the same at every point in the flow field. Non-uniform flow means the velocity changes from point to point.
Okay. And what about steady versus unsteady flow?
Steady flow means the velocity and pressure at any given point don't change over time. Unsteady flow means they do. It's kind of like the difference between a calm stream and a choppy ocean.
Right. And then there's compressible versus incompressible flow, depending on whether the density of the fluid changes during the flow.
Exactly. And we can also classify flow based on its dimensionality. Like one-dimensional flow is flow in a straight line, like in a pipe. Two-dimensional flow is flow in a plane, like over the wing of an airplane. And three-dimensional flow is flow in all three spatial dimensions, like the flow of air around a car.
Wow, it gets pretty complex.
It definitely can. But there are some fundamental equations that govern fluid flow, like the continuity equation and Bernoulli's equation.
Okay, tell me about those.
Well, the continuity equation is basically a statement of conservation of mass. What goes in must come out. So if you have a pipe that narrows, the fluid has to speed up to maintain the same flow rate.
Makes sense. And what about Bernoulli's equation?
Bernoulli's equation relates the pressure, velocity, and elevation of a fluid in a steady, incompressible, inviscid flow. It basically says that the sum of these three things, the pressure head, the velocity head, and the elevation head, is constant along a streamline.
Okay, that sounds complicated. What's a streamline?
A streamline is just an imaginary line that follows the path of a fluid particle as it flows. So Bernoulli's equation is telling us that as a fluid flows, if its velocity increases, its pressure decreases, and vice versa.
Interesting. What are some real-world applications of Bernoulli's equation?
Oh, tons. Like, it explains why airplanes can fly. The shape of the wing causes the air to flow faster over the top surface than the bottom surface, which creates a pressure difference that generates lift. And it also explains how Venturi meters work. These are devices that measure flow rate by constricting the flow and measuring the pressure drop.
Okay, that makes sense. Now, in the real world, we have to deal with friction, right? Like the fluid rubbing against the walls of the pipe.
Exactly. And that friction causes energy losses in the flow. We call these losses major losses if they're due to the friction along the length of the pipe, and minor losses if they're due to things like bends, valves, and changes in pipe diameter.
Got it. So friction is the enemy of efficient fluid flow.
Pretty much. But luckily, engineers have ways to minimize those losses, like using smooth pipes, minimizing bends, and choosing the right pipe size for the flow rate.
Makes sense. Okay, so now let's talk about fluid power systems specifically. Like, what are they and how do they work?
Well, a fluid power system is basically any system that uses a pressurized fluid to transmit power. It can be hydraulic, which uses liquids, or pneumatic, which uses gases.
And what are the advantages of using fluid power?
Oh, tons. Fluid power systems are relatively simple, they can be very powerful, and they can be easily controlled. They can also transmit power over long distances with minimal losses. Plus, they're pretty safe because the fluid itself acts as a lubricant and a coolant.
So, lots of advantages. What are some examples of fluid power systems?
Well, there's everything from the hydraulic systems that lift heavy construction equipment to the pneumatic systems that operate air brakes on trucks. There's power steering in cars, the hydraulic systems that control airplane flaps and landing gear, and even the systems that inject fuel into diesel engines.
Wow, so fluid power is everywhere. All right, so how do we actually generate that fluid power?
Well, for hydraulic systems, we use pumps, and for pneumatic systems, we use compressors.
Okay, and what are the different types of pumps and compressors?
There are two main categories: non-positive displacement and positive displacement. Non-positive displacement pumps, like centrifugal pumps, add energy to the fluid by accelerating it. They're good for moving large volumes of fluid at relatively low pressures.
And what about positive displacement pumps?
Positive displacement pumps trap a fixed volume of fluid and force it into the system under pressure. They can generate very high pressures, but they typically move smaller volumes of fluid than non-positive displacement pumps.
Got it. And what are some examples of positive displacement pumps?
Well, there are gear pumps, which use meshing gears to move the fluid, lobe pumps, which use rotating lobes, screw pumps, which use rotating screws, and vane pumps, which use rotating vanes. They all work on the same basic principle of trapping and displacing fluid.
Interesting. And once we have that pressurized fluid, what do we do with it?
Well, we use actuators to convert that fluid power into mechanical work.
Okay, so actuators are like the muscles of the fluid power system.
Exactly. And there are two main types of actuators: linear actuators and rotary actuators.
And what's the difference?
Linear actuators produce straight line motion, like the hydraulic cylinders that lift a dump truck bed. Rotary actuators produce rotary motion, like the hydraulic motors that turn the wheels of an excavator.
Okay, so linear is for pushing and pulling, and rotary is for spinning.
You got it. And these actuators are controlled by valves.
Valves. Right, I've heard of those. What do they do?
Valves control the direction, pressure, and flow rate of the fluid. They're like the brains of the fluid power system.
Okay, so they direct the fluid to the right place at the right time.
Exactly. And there are tons of different types of valves, each with its own specific function. Like, there are direction control valves that determine which way the fluid flows, pressure control valves that limit the pressure in the system, and flow control valves that regulate the flow rate.
Got it. And what about leaks?
Ah, leaks are the enemy. That's where seals come in. Seals are used to prevent fluid from leaking out of the system.
Makes sense. What are some common types of seals?
Well, there are static seals, which are used for stationary connections like O-rings and gaskets. And then there are dynamic seals, which are used for moving parts, like piston rings and shaft seals.
Okay. And what are some other essential components of a fluid power system?
Well, there's the reservoir, which stores the hydraulic fluid, and the accumulator, which is like a pressure storage tank, and filters, which remove contaminants from the fluid. And then there are all the pipes and hoses that connect everything together.
Right. And then there's the fluid itself.
Yep. The hydraulic fluid is super important. It needs to have the right viscosity, the right lubrication properties, and it needs to be compatible with the materials in the system.
So choosing the right fluid is crucial.
Absolutely. Okay, and lastly, your sources mention turbines.
Turbines, yeah, those are like big fans, right?
Well, they do have blades that spin, but they're a bit more complex than that. Turbines are machines that convert the energy of a moving fluid into mechanical energy, which can then be used to generate electricity.
Okay, so they're like fluid-powered generators.
Exactly. And there are different types of turbines depending on the type of fluid they use. Like, there are water turbines, wind turbines, and steam turbines.
Wow. So turbines are another example of how we can harness the power of fluids to do useful work.
You got.
Okay, so we've gone through a lot. We've talked about materials, their properties, and how their structure influences their behavior. And then we dove into the world of fluid mechanics and fluid power systems. It's incredible how these concepts tie together in the field of mechanical engineering.
It really is. Understanding the strengths and weaknesses of different materials is crucial for designing safe and reliable fluid power systems. And knowing how fluids behave under pressure allows us to build these powerful machines that can move mountains literally.
It's a fascinating field, and our goal today was to give you a solid understanding of these fundamental concepts without overwhelming you with too much technical detail. Hopefully you've gained some valuable insights into the world of mechanical engineering.
I think so. And as a final thought, think about this. With all the advancements in materials science and fluid power technology, what amazing new machines and systems do you think we'll be able to create in the future? The possibilities are endless.
That's a great question to leave our listeners with. Thanks for joining us on the deep dive.
Thanks for having me.